So if we're going to get our ST graph using our V equation, we have this formula. V is equals to ds over dt. We arrange this. We have ds is equals to v dt. And then substitute the value of our v. ds is equals to 3 halves times t squared dt. And then we integrate this. Again, from the origin t0, we have s and then t. This is just example. Some problems involves different or their initial acceleration or initial displacement and velocity and acceleration have values. So this is just an basic example. So we have s is equals to the integration of t squared s t cube. We have 3 halves t cube. We have 3 halves times 1/3. We have 1/2. So you have 3 halves and t cube over 3. Cancel. We have s is equal to t cube over 2. That is our equation for our displacement. T cube over 2 or 1/2 t cube. So a cube, how do we graph a cube? T and then s. Always remember, if a degree of 1, our graph is a diagonal line. For our 2, so example, this is our Cartesian plane. That is the graph. And then, if this is our Cartesian plane, the graph of a square is a parabola. It's like that. However, as you can see here in our VT graph here, so as you can see here, it's only half of the parabola. It's only here. That's because in our graphical method of analysis, we don't use all the 4 quadrants of the Cartesian plane. We only use quadrant 1 and the quadrant 4, since the quadrant 3 and quadrant 2 has a negative x-axis. Our x-axis is always t, so t or time can never be negative. However, velocity and acceleration and also the displacement can be negative. So we can also use our 4th quadrant. So anyways, so if the graph of a square is a parabola, the graph of a cube would look like this. It's just like a parabola, however, the other part of the parabola is facing downwards, and then the other is upwards. So this is the graph of a cube, just like a parabola. So we'll be able to graph t cube over 2 from 0 to 5. Let's see here. It has a 2.5, 0.5. Let's say this is what size font would be 30 to 65. We have from 0, and then at 1 second is 0.5, and then it slowly raised to 4, and then 13, 32, and then so on. So graphing your cube is just like graphing your parabola, since we're only using the other end of our graph of a cube. So this is our graph. So at time 5 seconds, our displacement is 62.5. So you can get the value by substituting the value of time to your t here. So this is how you create a graph for your graphical method of analysis. So if you are to read a graph, you have to know first its equation and then the behavior of the graph. So as you can see here, The velocity raised constantly, therefore its acceleration is constant. Here, you can see the acceleration is slowly has a constant raise or slowly constant raise, yes, uniform increase, which means its velocity is always in parabola form, as well as here. So another thing to remember is the line here for your ST graph is your equation. You have S is equals to D4. Also here for your V, V is equal to 2D. However, we can compute the distance or the total distance traveled by finding the area under the curve of our VT. Since we have this formula, V is equal to ds over dt, which means in order for us to find the distance, we have ds is equals to V dt. So we then have the formula, if we integrate this, we then have the formula S is equals to integration of V dt. Integration of V dt is just the area under the curve or under your graph of V. This is V dt. So in this case, it is a triangle. So its graph should be just if you integrate this to t squared, we have 2. So if we integrate this, or let's just say this is a triangle. So getting the area would be easy, or if there are any geometric shape present within your graph, you can just easily get its total distance traveled. So in here, its total distance traveled is 1/2 times 5 times 10, or its total, yes, total distance. So computing that, we have 1/2 times 5 times 10, we have 25. So its total distance traveled is equals to 25 distance, 25 meters. Okay, since you can also use dimensional analysis here, since this is 10, the 5 seconds is in seconds, and then 10 is in meter per second. Let's say cancel out, we have meters left. And then for acceleration, so your line here for the graph is your acceleration, and then the area under here would be your velocity. We have AT or ADT, since we have also the formula A is equals to dv over dt. By integration, we have dv is equals to a dt. Integrate this, we have v is equals to a dt, let's say. So in this graph, as you can see, we can also see a geometric shape, which is a rectangle. So the area of a rectangle is just base times height, or let's say the velocity is equals to 2 times 5. So the velocity is equals to 10 meter per second. So time here is 5. We have seconds, and your acceleration is 2 meter per second squared. We'll also use dimensional analysis here, cancel out, we have 10 meter per second. As you can see, our velocity here at 5 seconds is 10. So it is correct. So this is it for our basics for graphical analysis. Next, we're going to solve problems involving 2 or more governing equations.